Welcome to this video where I will show you how to perform simulation of 3D model of centrifugal pump impeller, which we was designed in previous video tutorial in part 1. And today we will continue this video tutorial and we'll create the mesh and paste boundary condition, set up it and make the simulation and try to predict the head and efficiency, hydraulic efficiency of impeller. So, and also we will find the power on the shaft. Okay, so let's start with ANSYS workbench. I use the version of the workbench 2020. It's not so important which version do you use for this, because ANSYS CFX is not changed with different versions. Okay, in previous video tutorial we have created the CFD domain in step format, so we will be using it for creation of the mesh. Let's use our workbench. Let's open it and just paste this step file to workbench. And in this workbench we can open the geometry in Design Modeler. Let's open it. Now you can see in tree the invert, and let's click generate and you will see the geometry of this impeller. So in the design modeler, let's define the boundary conditions and name it for creation of the mesh and for setup boundary condition in future. So let's choose this surface, click right mouse button and create name selection for this surface. Click this surface, click apply. You will define the one face here and let's set the name. Called it inlet. Okay, click generate and you will get, if you will choose this inlet here in tree, you will see the green surface on screen. Okay, let's repeat it again for another surfaces. We will define the outlet boundary. Let's make the name selection again, choose the geometry and name it outlet. Now we have the two different surfaces and let's define the wall and define it like shroud. Name selection, apply, you will get the four surfaces here and let's call it shroud. So the next step, let's choose the hub, create, just click the generate. We don't click it in previous and step so now let's choose the hub surfaces and make the creation of name selection. Called it hub, we generate, you will get the hub, shroud, inlet and outlet boundaries, and the one else surfaces will be the periodic surfaces. Let's choose these three surfaces, click name selection and click apply. It will be three surfaces and called it like pair 1. It will be periodic 1. And let's repeat this for another side of periodic surfaces. Click the name selection, apply, and call it pair to periodic tool. And now we have defined. Let's check it. It looks correctly here, and we have the hub, shroud, inlet, outlet, inlet, and another. Okay. And the last surface will be the wall of the blade. So we can to hide these faces. Just you can use the shift button on keyboard and choose the first and choose the last with shift on keyboard. And after that, let's choose it here, or just I click it again, choose it here, and a right mouse button, and you can to hide faces here, and you will get only blade. Let's choose this blade surfaces. Get leading edge, pressure side, suction side, and trailing edge. Okay, let's create the name selection for this and called it blade. We'll generate, and let's show again. I set the cursor for first inlet and for last with a shift, press shift on keyboard. Okay, and show hidden faces. And now we have all called names of the surfaces for future setup boundary condition in ANSYS CFX. So the second step will be creation of the mesh. So let's save our project. I will save it in my desktop, called it pump impeller. Click save, and after that let's go to mesh. Let's connect our geometry with mesh model and open the meshing module in ANSYS. Wait some time. And here we have our geometry with name selections in meshing model. In meshing model we have to set up the mesh for future simulation in ANSYS. So let's choose the mesh in tree, and in mesh we have to change the physics preference and set the CFD. Also you can to choose here the CFX. It will set some default settings for mesh here, and let's choose the mesh, insert, and let's set up the method for this geometry. Choose it on the screen, click apply, and set tetrahedrons. After that you can go to meshing, and for example let's generate some default mesh. Here we have the very rough mesh. Let's check the number of elements. Here we have 43,000 elements of the tetrahedrons, and let's decrease the size of global mesh element here and set it, for example, max size to 3 millimeter, maybe 6 millimeter I think will be enough. Okay, let's make the generation, and you will get some smooth mesh with 50,000 number of elements, and it looks not bad. Of course, for very accuracy results of CFD simulation, you have to perform mesh convergence. You have to increase the number of elements of domain and perform simulation again, repeat it, and you will get some performance characteristics of Impeller for different number of mesh cell size, and you can do then more elements you will set, then more accuracy in numerical point of view you will get results. Okay, let's choose this, and now of course you have the turbulent flow through this channel, and we have to set some layers, boundary layers on the walls. Okay, let's insert the inflations, it's called it in ANSYS meshing. So let's choose this body, and let's choose, for example, blade, shrub, and how. Let's set this coefficient of layers 0.5. It will be the half of global element length thickness, and let's set up, for example, 5 number of prismatic layers, number of layers, and set up the ratio. I will set 1.4. The coefficient, the size between the layers, increasing the size between layers. Okay, and let's perform the generation of mesh, and you will get here the some boundary layers. It looks here, you can see it. Okay, it looks correctly, so we have not much number of elements here. I think for test simulation it will be enough. So let's close this and close the design modular, and just to save project. After that, let's open the CFX and connect our mesh model with CFX, and click right mouse and set update, perform update. And let's open the CFX. So in ANSYS CFX, we have to set up boundary conditions, and let's go to boundary turbo mode. It will perform the setup in something like automatically mode for turbo machineries. And let's choose this pump and rotation axis. We have now, if you will change it, you will get wrong direction. We have to set Z direction. Okay. Now we have to set X direction here. Okay, it's correct direction. we have the steady state, access visibility, set it, and here we have the one domain, it component called it in CFX, it rotor 1, and let's set the rotation per minute. In previous video tutorial we set the rotation speed 3000 RPM. Let's set it here, and how can you see on the screen, you have this arrow, and we have the contour rotation. We have to change it into the right direction of rotation, and for this, for changing of rotation direction, we can just paste minus, and you will get the right direction of centrifugal pump impeller. Here we have some automatically region information. It's hub, shroud, plate, inlet, outlet, and for periodic we can set the pair 1 and pair 2. It will automatically create the boundary conditions here. After that, let's go to next step, and let's set up the fluid parameters. It will be just water. Reference pressure you can set 0, and we have to set the inlet outflow boundary conditions. Let's choose the pressure total and mass flow outlet boundary condition. Let's set the 1 atmosphere in our inlet boundary here, and we have to set up the number of fluid volume flow rate. We have in previous video tutorial 150. Let's paste it, but here we have the mass flow rate, here we have the volume flow rate, so we have to recalculate it meters power 3 2 kilograms per second. So for this, let's go to the calculator and just convert the volume flow rate to mass flow rate. You have to delete it by seconds, hours to seconds convert, and multiply this meter power to the power of 3 to we have to multiply it by density. It will be kilograms per meter power 3. Okay, and you will get the mass flow rate. It will be 41.5. I will just copy this and paste it here, but it doesn't work. We have to manually set this value. 41.5 416. Okay, maybe the last one will be 7. Okay, so the parameters, it will be default settings. Here we have the per component, we have the 7 blades, 7 components here, but you can set the per machine. It will multiply automatically divide this mass flow rate to 7 number and set for this boundary this mass flow rate divided by 7. Okay, so let's go to next, and we have here the interfaces. It will be only one periodic between this and these surfaces, periodic 1, periodic 2 sides. Okay, let's go to the next, and you will get the boundaries. It will be blade, hub, inlet. You have the stationary frame with total pressure 1 atmosphere, and here we have the mass flow rate for all sectors, and R1 shroud, no slip wall. Okay, so let's go to the next, and let's click finish. And so now we have to set up the boundary conditions here, and let's go to solver control, and in the solver control we can set up number of iterations. For example, the maximum number, let's set 1000. Residual target, it's accuracy of simulation. Then if you will set the very rough value, you will get very rough results. It will be something like garbage, and we have to decrease the criteria of residual target. Okay, timescale factor we set the default, and high resolution for advection scheme, and for turbo balance numerics first order. It's enough accuracy. High resolution it's second order accuracy. Okay, so let's set first order and click OK. Also, we have to check which value of head we have for pump impeller in process of simulation, because the CFD simulation is iterative process. So, and for watching which value of head we have in process of simulation, we have to calculate the head. For this purpose, we can create the expression and call it head. Okay, and in the head we have to calculate the head of pump impeller. For this purpose, we can define the head of pump impeller. It's just a difference between outlet pressure and inlet total pressure, average, and we have to average the total pressure on the outlet boundary and inlet boundary. So let's go to the functions. Let's choose the mass flow average absolute. Here you will get the averaging on the boundary, and here we have to paste the what variable we will be use for averaging. We want to use the total pressure in absolute coordinate system. Just choose this, and let's choose the boundary. The boundary here is outlet, but in ANSYS CFX it's called R1 outlet. I will show you just to apply here R1 outlet. If you will go to outline, you can see that for our boundaries we have another names. It will be R1 outlet, and also for R1 inlet we'll be using the difference between these boundaries for calculation of head. So let's just copy this, Ctrl C minus Ctrl V, and change the name here to outlet to inlet. Let's define all this expression to density. It will be 1000, and to G, it's a gravity constant, and click the apply. You will get the head of this pump impeller. So let's click outline, click save, and let's go to output control, go to the monitoring, monitor object, create one item, and let's paste here head, and just for h we have to paste here the expression of calculation of head. Let's choose here expression, and in right mouse click button and choose the expressions head. Click apply and OK. And here, if you will show this tree, you will get the head monitor point. So let's save it and close the ANSYS CFX, and let's start the simulation process. I have the Ryzen 3900. This CPU have 12 cores, and if you have another number of cores, for example 8 cores, you have to set it in Intel MPI local parallel to CPU cores. I set all my cores to be 12. You can to use, for example, 1 core or 2 core, 4 or another value which you have. I have this maximum number, and just don't use another settings. Simple start run. And wait some time, and the simulation is very fast because we have the small number of cells. And here we have the residuals, the different values, and here we have the number of head of impeller. So now we have the very good value of head, because in our report we have the 103 meters of head. For impeller we have this, because we have some losses for all pump. It empirical expression define 7 meters here, something like losses, hydraulic losses in stationary elements like stator vanes or volute or another types of outlet elements. And here we have this value predicted by empirical calculation, and here we have the simulation. Its head is really not much difference with this value. Let's check the 122 divided by 111, and you will get the difference 10%. Okay, I think it value will be smaller. And how can you see the residuals is really very small. For turbulence residuals we have also small, and the value of head is something like 122. If you will change the range of this plot, let's set up it for last 500 iteration, you will get something like periodic oscillation of this chart. And we can use the range between 124 122. It's not much. Let's just stop the simulation and just use it this value of head like prediction of simulation. And also let's just to see how looks the flow in pump impeller, and let's check the power on the shaft and hydraulic efficiency of pump impeller. So let's close it, the ANSYS CFX, save the project, and let's click open the results. It post-processor. Here we can to create the different beautiful pictures. For example, fluid velocity fields, prior fields, or another. Let's just you can to work with this post-processor manually, creates, for example, the plans, create the vectors, or you can use for typical tasks. For example, its typical task is rotor simulation of pumps, turbines, compressors, or nozzle. You have some default reports. We can choose the report templates, and here we have the different templates for analysis of the pictures and fluid flow through the domain and another. And here we have the pump impeller, and just to click the pump impeller report and click the load this report, and ANSYS automatically generate these fluid parameters, and click OK, and we can go to report viewer and wait some time. And let's go to here and let's check the shaft power. It something like 52 kilowatts, and here we have the 54 kilowatts. It's really similar, and the predicted efficiency we have the 95. It means that we have the good pump impeller, but here we have the prediction full efficiency. This efficiency include outlet hydraulic losses, inlet hydraulic losses, mechanical losses in bearing and disc losses. Here we have the almost ideal efficiency of impeller. It's good value of efficiency for impellers. Here we have the distribution of pressure around blade for hub, average line of blade, and shroud span. Okay, here we have the different plots and different pictures. For example, how looks velocity fields for different height of blade, hub, average span, and shroud span, meridional averaging of fields. Here we have also it accompanied of meridional velocity and different other slices. Here we have. Okay, the simulation was performed successfully, and in the next video tutorials I think I will perform the open form simulation of this impeller, and we can compare the empirical prediction, ANSYS CFX prediction, and open form prediction of head and power on the shaft, for example. So thank you for watching, subscribe to the channel, goodbye.